Over the past century, physicists have been intrigued by black holes, with the idea gaining significant momentum around 1916. These cosmic anomalies are among the most intriguing and confusing phenomena we know of. Their immense gravitational forces create an intersection beyond our grasp. A black hole, which could weigh as much as 2 to 4 times our sun's mass, remains a mysterious presence in the universe. Despite decades of intense research, our understanding has expanded from virtually no knowledge to piecing together numerous additional details. Discoveries in recent years, including a breakthrough by Michio Kaku, have uncovered shocking insights into the interior of black holes. These findings might challenge our long-held beliefs and suggest new perspectives on the nature of these celestial bodies. This brand-new data opens doors to deeper investigations into what may have been previously overlooked. Join us as we venture further into the captivating world of black holes and uncover what lies hidden within the vast and enigmatic universe. What exactly are black holes? Before we examine the most recent findings by Kaku, it is necessary to return to fundamental knowledge about black holes. While most of us have a general sense of what a black hole is, some important aspects remain hazy. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At the time, the idea was purely conceptual. It wasn't until around 50 years later that evidence confirmed that black holes are real entities in space. This discovery occurred in the 1960s when scientists studied the star Cygnus X-1, a bright celestial body that emits X-rays. Observations showed that these X-rays fluctuated erratically, as if being drawn into a dense, invisible mass. This mass was later referred to as a black hole. This finding changed our perception of the universe. It was mind-boggling because it demonstrated that black holes were not merely figments of Einstein's imagination, but real-world objects worthy of further study. Following this groundbreaking revelation, scientists worldwide embarked on a global search for more information about black holes. Their efforts led to the realization that the Milky Way alone could contain approximately 100 million black holes. However, due to the difficulties in recognizing them, this estimate remains uncertain. Despite their elusive nature, scientists believe that many of these massive entities are hidden within our galaxy, making it even more crucial to understand them. The core concept is that gravity exerts such massive forces that anything entering their vicinity is trapped in a singularity, a point where the laws of physics, as we know them, cease to function. In simpler terms, black holes act like gigantic vacuum cleaners, pulling everything into them. One of the most terrifying aspects of studying black holes is the idea that if someone were to enter one, they would gradually stretch out and become a singularity, their body torn to pieces by extreme gravitational forces before reaching the point of complete annihilation. It is best to stay far away from one. Though black holes are scattered across the universe, the closest known one is nearly 500 light-years away. Still, its proximity raises significant concerns. In 2021, scientists achieved a historic milestone by obtaining the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent capturing images and aligning them to create a single, coherent picture. As more data was gathered, researchers determined that black holes consist of 3 distinct layers, contradicting the misconception that they are merely vast voids. 1. The event horizon. This marks the point beyond which nothing can escape. Once something crosses this boundary, it is inevitably drawn toward the black hole. 2. The photon sphere, a region where light itself becomes trapped, unable to escape due to the intense gravitational forces at play. 3. The singularity, the core where all matter is compressed into an infinitely small point, causing the very fabric of reality to collapse and the known laws of physics to break down. Even more fascinating is the fact that each black hole is unique in its own way. While they follow the general 3-layer structure, their behavior can vary significantly, making them particularly challenging to study. Traditional scientific methods don't apply to black hole research. Instead, scientists rely on indirect methods, such as examining the radiation they emit or observing the gas and dust swirling around them. Sending a probe directly into a black hole would be futile, as anything crossing the event horizon is inevitably drawn toward the singularity and crushed into oblivion. Due to this unavoidable outcome, billions of dollars cannot be spent on probes that would meet their end before supplying any useful information. How do black holes form? Black holes are thought to form when massive stars collapse in on themselves. As a star burns its fuel, it can no longer produce enough energy to counteract the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of black holes, NASA scientists have focused on the center of the universe, particularly the M87 galaxy. There, they observe a powerful vortex of hydrogen gas rotating at a staggering rate of 1.2 million miles per hour. The outward force should have caused this gas to disperse, but instead, it remained unaltered, indicating the presence of a massive object at the center, likely a black hole. This object is thought to have a mass of 3 billion or more times that of our Sun. The role of wormholes. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to describe the behavior of rotating black holes. He argued that instead of collapsing into a single point, a spinning black hole forms a thin ring-like structure known as the ergosphere, a rotating band of matter. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through space-time, connecting distant parts of the universe, or even parallel universes. To grasp the concept of a wormhole, it is essential to understand Einstein's description of space-time, a four-dimensional fabric distorted by objects with mass. This distortion creates gravitational fields that influence how other objects move. Imagine space-time as a piece of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut represents a wormhole, a potential passage linking distant locations almost instantly. Although wormholes remain a theoretical concept with no direct evidence, they are a natural consequence of general relativity. However, they are inherently unstable, meaning they would collapse quickly if they existed. Despite this, the idea that wormholes could serve as gateways to different parts of the universe, or even different points in time, has captivated physicists for decades. The search for unified theory. One kind of theoretical wormhole, known as the Kerr-Rosen wormhole, has been a subject of interest. Named after Roy Kerr, this hypothetical wormhole could theoretically connect two distant points in space-time, possibly linking different universes or timelines. While the idea of using wormholes for interstellar or time travel is enthralling, there are significant challenges. As we continue to investigate the mysteries of black holes, one thing is certain. The more we learn, the more we realize how much there is still to discover. Black holes are not just points of destruction. They're locations of extreme physics, where the fundamental laws of the universe are tested to their limits. Recent advancements in observational technology have allowed scientists to gather more information about black holes than ever before. The Event Horizon Telescope, EHT, a global network of radio telescopes, provided the first-ever image of a black hole in 2019. This was a historic milestone, confirming theories about black hole structure and behavior. With future improvements in imaging technology, we may soon be able to capture even more detailed visuals of black hole activity. Another promising area of research involves gravitational waves. First detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, these ripples in spacetime are produced when two black holes collide. By studying these waves, scientists can gain insight into the mass, spin, and interactions of black holes, offering valuable data that was previously inaccessible. Black holes and the nature of time. One of the most intriguing aspects of black holes is their relationship with time. According to Einstein's theory of relativity, The immense gravitational pull of a black hole causes time dilation, meaning that time slows down for an object approaching the event horizon. If an astronaut were to fall into a black hole, an outside observer would see them slow down more and more, never actually appearing to cross the event horizon. However, from the astronaut's perspective, they would experience time normally until reaching the singularity, where the laws of physics break down. This has led some physicists to speculate about whether black holes could serve as natural time machines. Theoretical models suggest that the extreme warping of space-time around a black hole might allow for time loops or even backward time travel. However, these ideas remain speculative, as they would require stable wormholes or exotic forms of matter to become feasible. Black holes and the fate of the universe. Understanding black holes is also crucial to understanding the ultimate fate of the universe. Some theories suggest that as the universe expands and galaxies drift apart, black holes will continue to grow, consuming surrounding matter. Over trillions of years, these black holes may slowly evaporate due to Hawking radiation, a theoretical process proposed by Stephen Hawking. Hawking radiation suggests that black holes are not entirely black. Instead, they emit tiny amounts of radiation over time. Eventually, this radiation would cause the black hole to lose mass and disappear completely. If true, this means that in the far, distant future, all black holes will eventually vanish, leaving behind a dark, empty universe. The next frontiers in black hole exploration. While direct exploration of black holes remains impossible with current technology, scientists are developing new methods to study them. Some exciting upcoming projects include the James Webb Space Telescope, JWST, launched in 2021. JWST has the ability to observe distant black holes and their surrounding environments in greater detail than ever before. Next-generation gravitational wave detectors. Future observatories like LISA, Laser Interferometer Space Antenna, will help detect more gravitational waves, providing insights into the formation and behavior of black holes. Quantum gravity research. Scientists continue to develop new theories, such as loop quantum gravity, which may help bridge the gap between quantum mechanics and general relativity, offering a deeper understanding of black hole interiors. Conclusion. Black holes remain one of the most mysterious and awe-inspiring phenomena in the universe. They challenge our understanding of physics, time, and space, pushing the boundaries of what we know. As technology advances, we are closer than ever to unlocking their secrets. Whether through gravitational waves, space telescopes, or revolutionary new theories, the study of black holes is sure to reshape our understanding of the cosmos. As we continue our journey of discovery, one question remains: what other cosmic wonders might we uncover along the way? Extraordinary complexity and the possibility of being gateways to other dimensions, as some theorists suggest, make black holes one of the most fascinating subjects in astrophysics. Whether or not they possess the key to comprehending the most important aspects of reality, black holes remain a crucial area of study. As our theories and tools advance, so will our comprehension of these mysterious objects. Looking ahead, the next significant obstacle will be refining our methods for observing black holes. One of the most significant developments in recent years has been the observation of gravitational waves. Gravitational waves are fluctuations in space-time caused by the acceleration of massive objects, such as the merging of black holes. By detecting and analyzing these waves, scientists can study black holes and other celestial objects in ways that were previously unattainable. The identification of gravitational waves has already provided revolutionary insights into the dynamics of black hole mergers. It is likely that future experiments will produce even more discoveries. In addition to gravitational waves, another promising area of study is the use of advanced imaging and telescope techniques. The Event Horizon Telescope, EHT, which captured the first-ever image of a black hole in the M87 galaxy, is an illustration of how cutting-edge technology can shed new light on black holes. By combining information from several radio telescopes around the world, the EHT was capable of taking a picture of a black hole shadow, offering a glimpse into one of the universe's most mysterious phenomena. As technology continues to improve, it is likely that we will be able to observe black holes in even greater detail, revealing additional information about their structure, behavior, and role in the universe. The study of black holes is not just about understanding these bizarre objects in isolation. It also involves uncovering the fundamental principles that govern the universe. Black holes are at the heart of our understanding of space-time, gravity, and reality itself. When we study them, we're not only investigating these cosmic giants, but also the laws that shape the universe in its most extreme conditions. The future of black hole research. The study of black holes is entering a new era, driven by technological progress and theoretical breakthroughs. While past research has largely been based on indirect observations and theoretical models, the coming decades promise direct and detailed studies that could change our perspective on these cosmic giants. Advancements in observational techniques. One of the most exciting prospects in black hole research is the improvement of observational instruments. The Event Horizon Telescope, EHT, provided the first-ever direct image of a black hole, but future versions of such telescopes could capture even sharper and more detailed images. Projects like space-based interferometers and next-generation radio telescopes could reveal finer details of black hole structures, including potential deviations from Einstein's general relativity predictions. Moreover, gravitational wave astronomy, powered by LIGO and Virgo, is anticipated to become even more precise. Future detectors, such as the Laser Interferometer Space Antenna, LISA, will operate in space, enabling the detection of gravitational waves at lower frequencies. This will allow scientists to study supermassive black hole mergers throughout cosmic history, shedding light on the role of black holes in galaxy formation and evolution. Black hole physics and quantum mechanics. Despite the success of general relativity in describing black holes, it remains incomplete without quantum mechanics. One of the greatest challenges in modern physics is the unification of general relativity and quantum mechanics into a single quantum gravity theory. Black holes provide the perfect testing ground for such theories because they involve both extreme gravity and quantum effects. One key puzzle in black hole physics is the information paradox, first proposed by Stephen Hawking. According to Hawking's calculations, black holes emit radiation, now called Hawking radiation, and eventually evaporate over time. However, this raises the question, what happens to the information about the matter that fell into the black hole? If the information is lost, it would violate fundamental principles of quantum mechanics, which state that information cannot be destroyed. Many theories attempt to resolve this paradox. The holographic principle proposed by physicists such as Gerard T. Hooft and Leonard Susskind suggests that all information about a black hole's interior may be encoded on its event horizon, much like a hologram. Another theory, the firewall hypothesis, proposes that a highly energetic firewall exists at the event horizon, preventing information loss. Quantum entanglement and wormholes. Recent research suggests that quantum entanglement, the deep connection between distant particles, might play a crucial role in preserving information. Some theories even propose that black holes could be connected to other parts of the universe via wormholes, potentially resolving the information paradox. While no single theory has been definitively proven, ongoing research in quantum gravity, string theory, and black hole thermodynamics continues to push the limits of our understanding. Are black holes gateways to other universes? An additional fascinating possibility is that black holes may not be the ultimate endpoints of matter, but rather cosmic tunnels leading to other parts of the universe, or even other universes. Some variations of Einstein's equations suggest that wormholes, hypothetical bridges through space-time, could exist. While no direct evidence for wormholes has been found, future studies might reveal indirect signs of their existence. If some black holes behave unexpectedly, emitting unusual radiation patterns or showing anomalies in their gravitational influence, they could hint at ties to unknown dimensions or parallel universes. Some physicists speculate that what we think of as black holes could actually be white holes, theoretical objects that expel matter rather than absorbing it. In this scenario, Material that enters a black hole in one part of the universe may reappear from a white hole in another. While this remains speculative, advancements in our understanding of gravity and quantum mechanics could eventually move these ideas from science fiction to scientific theory. The role of artificial intelligence in black hole studies. With the massive amounts of data collected from gravitational wave detectors, telescopes, and particle physics experiments, artificial intelligence, AI, and machine learning are playing an increasingly important role in black hole research. AI algorithms can detect gravitational waves more quickly and with higher precision, process vast amounts of astronomical data to identify black hole candidates, and model the effects of black hole mergers on spacetime. As AI technology continues to evolve, it will likely revolutionize how we study these cosmic giants. Conclusion. The study of black holes remains one of the most exciting and challenging fields in modern physics. With each new discovery, we move closer to unraveling the mysteries of these cosmic giants. Whether through gravitational wave research, advancements in imaging technology, or the development of new theories, black holes continue to captivate both scientists and the general public.